Thank you everyone for coming. So today, Chaitanya and Joshi will be joining us, the final year PhD student in computer science, supervised by Pietro Liao, who's also, I think, quite connected to some of us here at the VSU. His research is about deep learning foundations for molecular modeling and design. He's previously worked at Pressing Design, Genentech, and FAIR on the same. Chaitanya, the floor is yours.
Thank you for inviting me. Yeah, it's a pleasure to be here. I'm Chaitanya, and this is work that I did during an internship at Meta's chemistry team for All-atom Diffusion Transformers. Why does Meta have a chemistry team? So the reason is that first it started as a moonshot, like they want to contribute to science generally, and second, they also make lots of hardware such as VR headsets. And if you ever use one of these, then you know that they're clunky and they have a really short battery life. So revolutions in material science are needed to, make these things useful. And this team has actually contributed to, potential candidate materials and next generation VR headsets. And so this work really is more about architectures, more about machine learning ideas. And I'll like start by just giving a brief intro of me. So I work mostly on models, molecular modeling in general, deep learning techniques and generative models. The other part of my research, which I'm not talking about today, is about translating these tools to design RNA molecules. And we've been actually testing some of these with another MRC unit over at the LFB nearby. So this is what I do. And, this talk is about the first part. So foundation models for chemistry are a big buzzword right now. And, the idea is that there are a lot of molecular systems in the biological and physical world. So materials around us, molecular systems, they're all made out of atoms, and we want to build models that can do useful things for them. And by useful things, I mean, for instance, something as simple as predicting properties. So, you take a system, maybe it's a protein ligand interaction or, any other kind of chemical system, and you predict some properties about it. Or, for instance, you may want to predict how it moves. You may want to simulate its dynamics. That's also a predictive task. And one of the ideas in the field, or one of the excitements in the field right now, is build one model that can do this for all kinds of chemical systems, like whether it's an antibody or a protein or a small molecule or maybe like some inorganic material. Like we want one model such that it's very simple for to apply them. So this has been happening, and yeah.
Do you think it's the right approach to use one model for all these?
I think like it's the winning approach in the rest of machine learning right now, right? So natural language processing, vision, speech, like they've all benefited from unified models across multiple modalities and have seen evidence of transfer learning. I think we haven't really seen that very clearly for molecular systems just yet, but I think like that's the bet people are making, right? That like if you crack the recipe, if you get the right architectures and you're able to scale data sets, then you can see this kind of transfer learning. I'll touch a bit upon this as well, like why we want to do this. The other thing you can like use these tools for is generative modeling. So here, like you train on a data set of existing molecular systems, and you're going to then generate or sample new ones, which basically follow the same data distribution. So they're realistic, but they're sufficiently novel. And like one example of this being used very successfully recently, or like where we're starting to see a lot of excitement is antibody generation or antibody design. So, being given some new epitope and being able to generate potential binders for that epitope purely on a computer and with some success rate, some quite low success rate, but still with some amount of success rate, you're able to get like experimental binders for this. So several companies have been spun out and several sort of pharma companies have started their own research efforts basically around building these kinds of models. I think like what we haven't seen for generative models though is this kind of idea of unification or learning from multiple sources and showing that you can learn something new across different sources. And I also wanted to say one word about how I talk about predictive models and generative models. But when you really use these models, like in industry or for real applications, you combine these models. So you may be generating candidates and then you may be ranking or scoring them with your predictive models. So it's kind of like a whole pipeline. It's not necessarily one model. So the goal of this work and like the broader vision of the field, right? Related to what you were asking, Luca, is like you want to train on large and diverse datasets with the idea that you can learn something general. So if you believe that there is something general across these systems, which I think in the case of molecular systems, there might be, right? Like they're all built out of atoms and there is at least like some shared underlying physics to them, right? Then you can learn some general representation, which you hope will be useful for novel and data scarce scenarios. So scenarios where perhaps you have too few data points to train from scratch could benefit from this kind of setup. Or scenarios where, perhaps combining two related data sources improves performance on both. We've seen this in language where, now this is like just anecdotal, right? But multiple papers have claimed when they train LLMs on more math, like mathematical content, they get better at programming. And hey, like that's quite weird, right? And we want to see if there are like analogies to in science and biology, right? And I think like that's the vision, that's the bet. Of course, like we shall see how it plays out. I think, and I mean like the pessimistic or skeptical side of this is that I think like there are very few demonstrations of success of this bet for scientific tasks. When people properly benchmark, right, then they find that the big sort of universal or foundation model is outperformed by a model trained specifically on a data modality. So far, like general statement, but we've seen this in a few different scientific tasks. So that's why like the skepticism is welcome as well, right? So that's what the talk is about. Like it's about these sort of 3D generative models and perhaps like how we could unify them. And just to like give you background on what exists today, right? The current state of the art for generating molecular data is based on diffusion models. Are you guys familiar with diffusion models? Like, so generally, what these models do is they're sampling from a data distribution, and how they do it is through starting with some noise, which is usually Gaussian noise. In the case of images, it's just pixels with random colors. And then you train a network to iteratively sort of correct this or, like learn to clean this data. And this is why they're called denoising diffusion. And in the case of molecules, right, like this approach has been quite successful. In fact, like the Nobel Prize for protein design, for instance, was given out on like very similar approaches, which, for instance, in this GIF, you can see that they're doing something called motif scaffolding. So you may have like some functional motif, and you may want to build like the rest of the protein around that functional motif. And they're able to do this very successfully at the Institute of Protein Design using these kind of diffusion models. So here's how they work. And to give you an example, I'll start with small molecules. So here, right, like for small molecules, what they do is, again, they start with noise. And here, the notion of noise would be scrambling the coordinates of this molecule, as well as scrambling the elements or the types of atoms present in the molecule. And this makes it, this makes it completely unphysical, obviously. And then as your network denoises it, it ends up at a physical molecule. So basically, you jointly diffuse atom types and 3D coordinates. The issue with this is that atom types are categorical, so there are like about 100 different types of atoms, whereas your coordinates are floating point values, which diffusion is usually quite good for floating point values, like images and pixels and sound and so on are floating point values. But it's not obvious how to also diffuse categorical data. And that makes for quite a complex architecture, that makes for quite a complex model. It works decently, but it's still a little bit it can be continuous noise addition, like you start from the valid structure and you continuously add noise. That's one formulation. Another formulation is you could also literally just sample from a normal like Gaussian distribution. People have shown that both formulations work. The second formulation is called flow matching, but it's roughly the same thing.
I have a question about that.
Yeah.
Training diffusion models on image data makes sense because you have like a smooth transition between noise and the image almost.
Yeah.
Whereas here, for example, if one step I change the type of a particular atom, that might completely change the meaning of the structure.
That is one of the motivations for this work as well, is that like essentially maybe there is some meaning to like the coordinates being noise, but the atom types being noise is really unphysical or like it leads to these transitional states which are not realistic molecular systems, right? So like that analogy to like all the success in the rest of deep learning kind of doesn't hold here or doesn't hold so well. Obviously, people are trying really hard to like get this to work as well, but I think like there is an argument to be made that diffusing jointly multiple types of data is at least mathematically not really nice. It requires some tricks to kind of get it to work. And the situation kind of worsens. So like when you want to generate crystals or materials generally, or any kind of periodic system, then you have this additional notion of a unit cell or essentially a box that you draw around your system, and then you can infinitely tile that box. That kind of gives you this notion of a slab or of like infinite periodicity. So now you need to do diffusion on what's called a manifold or a joint distribution of atom types, coordinates, and then the lengths and angles of this unit cell. So again, like your loss functions and your architecture for doing diffusion start to get quite complex and start to diverge a lot from the molecular side of things. When you look at biomolecules, so things like AlphaFold or the protein design tools, there's a different sort of complexity there. So there, what people have been doing is they've been grouping atoms in, say, residues together. So in a single amino acid, you can group it together, and you can treat it as a rigid body. And then now you can diffuse or you can generate the position as well as orientation of this rigid body, from which you can infer the coordinates of all the members of this group of atoms. But again, you can see that like it adds complexity in the sense that now you're diffusing over coordinates, positions, as well as orientations. So essentially, again, like your diffusion formulation here is completely different from molecules and crystals. And it's really hard to kind of think of a joint architecture, at least in the current paradigm. So our research question was, how do we build a unified generative model for all chemical systems? What's the architecture that is sufficiently general such that you can generate multiple kinds of systems from it. So the first idea is really simple. Like we can think of all these systems as collections of atoms, right? So like we can then embed or encode these systems into latent representations. And the idea is that embedding or training a neural net to take as input both molecules and crystals and biomolecules and so on will improve performance across all these types of systems. This is not a new idea. I think like people have shown this for predictive models, as I said at the start, that like there have been examples of predictive models trained on both molecules and materials that improve performance. But we wanted to think about how we could do it for generative models. So to do that, you kind of need to come up with an input representation that's shared across these two types of systems. So a crystal, which is this periodically repeating system, would be represented as follows. So if you have n atoms, then for each atom you have an atom type, its coordinates, as well as these lattice parameters or these unit cell parameters. And using those parameters, you can infer what are called fractional coordinates, which have been shown to sort of be more amenable for machine learning as a representation. But basically, there's not that much difference from just normal coordinates. And then when you think about molecules, and this sort of extends to biomolecules as well, you don't have this notion of periodicity. So you just have the atom type and 3D coordinate, and you can set the sort of periodic data types to null values, but you still have like a shared input format that you can process your data in. So, like when you're doing machine learning with these multiple data sources, you can kind of pre-process them into one format, which then makes everything easier and makes it possible to work with them. And we can do, and as I said, like this has been done. We can do this, right? Where we take these systems, we take their attributes that we just discussed, like their atom types, their coordinates, and so on. And we can embed them using a graph neural network or a geometric graph neural network in this case, because we have 3D data. And we can learn some latent space, and here it's showing you like how the latents are distributed. Generally, no. I think these shapes are to like illustrate that there is this notion of batching in this model, although it does make the figure a little bit more complex. But sometimes like what you can say is that you can also pad up to some maximum n as well. I think what happens with these architectures like GNNs and so on is that they're completely like, they're agnostic to the size of the input. So that makes it possible to train on smaller n and use that on larger n as well. So like, yeah.
Before you have the atom types and the coordinates. You have to specify the links and the ones maybe have structure you have around.
Yeah, so generally, like there are two ways. The first way is that you can you kind of build some radial cutoff or radial neighborhood around each atom. So you say like we want to learn embeddings for each atom with respect to, say, every other atom within 6 angstroms or 9 angstroms of itself. And that's what graph neural networks do, because that's how you construct this notion of a graph. You construct this input graph through like this local radial cutoff. And this is a good assumption because, a lot of molecular phenomena are often local. But there's a new emerging idea in the field, which says that if you have enough GPUs, then you can assume that everything is connected to everything. And you can let the model kind of learn this notion of whether locality is important or not. And that, you could call that a transformer network or a graph transformer network. Like nowadays, as we're starting to scale these models up, people are attracted to that idea as well. Yeah.
So to understand, so you also create a graph and then you train that what is parameters that you have within the space, or you also start with its graph.
I think like this notion of like creating the graph is almost deterministic. So it's not part of like what's trained, like what's trained are the weights of the neural network that's going to process that graph. So that graph can change across systems. So if you have one molecule, you may have a given graph.
Why do you mention then that it's the stuff that have predictions?
I think that's what makes it deterministic, right? So like if you train your model, so if you train the weights of your GNN on, say, a radial cutoff of 6 angstrom, right? And then you go to 9 angstrom and it suddenly stops working. Okay. So that's the reason. So like just a word on these geometric GNNs, like the idea with them is like, these are models that enforce some physical symmetry, some physical constraints. So, like, for instance, if you give it rotated versions of the same molecular system, it'll learn embeddings or representations that respect these physical symmetries. So as I said, like an interesting idea in the field now is to just, instead of building like a GNN, which can be quite involved, you can just take a standard transformer and do the same thing, like you can learn embeddings. And perhaps through data augmentation, as well as through scaling, you can, instead of building in a lot of these ideas of locality, of rotational symmetry, and so on, you can learn these ideas from data. And this is working quite well too. In our work, we kind of, we tried to ablate this. We tried to see which one worked better. So that was about like thinking about everything as atoms. The other idea here is to then do diffusion or do generative modeling in the latent space of a joint encoder. So since we can encode things to a latent space quite well, and we've seen that this is successful, can we then do generative modeling on these latents and then reconstruct back to valid molecules or materials? And this idea, right, has been really successful for computer vision and videos, audios. So this idea of latent space diffusion is what's powering a lot of these kind of tools like suddenly forgetting its name, Stable Diffusion, for instance, or Sora from OpenAI. Like these are all latent space diffusion, with the idea being that doing generative modeling in some compressed latent representation is better than doing it in sort of raw pixel space or raw audio space and so on. So this is what we call our model, All-atom Diffusion Transformer. It's based on diffusion transformers which are used in Sora. It's a two-stage pipeline. This figure looks really complex, but I'll walk you through it stage by stage. So the first stage I already kind of talked about. You take your molecular system and you encode them, you learn some latents. And then you can decode back to valid molecules. This is an autoencoder, and the idea is that you use a very small latent dimension, D, in this figure, which basically forces the model to compress or bottleneck a lot of the information into a small compact latent. And then you can decode back and you can train for reconstruction. This is a simple task. And essentially what it does, right, is all these input and output representations are what you can call like multimodal data, right? Like they're different kind of, there's categorical values, there's continuous values. And through your autoencoder, you can kind of compress all that into small floating point latents. I think this is a general idea that potentially could be applied to other fields of ML as well, particularly like scientific fields where you do have this notion of integration of data modalities, right? So all this autoencoder does is it integrates into data and then decodes back uncompressed. And essentially these latents can be equivariant, can preserve symmetry. You can use GNNs for them, or you can just learn the symmetry using transformers and data augmentation. Stage 2 is that once you have these latents, you then freeze your autoencoder, you stop training it, and you're then going to train your generative model. So what you're going to do is you're going to take your training set and compute latents for every molecule or crystal in your training set. And then you're going to train a diffusion model on those. So instead of training diffusion on directly a molecule or crystal, you're going to train it on the latents for that molecule or crystal. With the idea being that it's easier to train on latents. And then once you have sampled new latents, once you've trained your generative model, then you can take your sampled latents and then use your decoder from part 1 to get back balances. So it's a two-stage process. First stage compresses all these sort of multimodal data into latents. Second stage does generative modeling of latents, which is a little bit like which was a little bit unintuitive, but has been shown to work really well in other fields and sort of overcomes this issue that we talked about of having these different data types and so on. And then you can reconstruct back using a decoder. The architecture being used here is a diffusion transformer to do this kind of denoising as well. I think this is kind of standard stuff that I won't talk too much about now. But I guess one thing to say is like with these diffusion transformers, like what made them so successful for Sura and stable diffusion is that you can condition them. You can give text prompt, or you can give some desired properties for your molecule, for instance, and they're quite successful at generating outputs with these desired properties. We haven't done much of that in our paper, which was like a lot more about the architecture. But so just to say that I think conditioning latent diffusion models has been shown to be quite successful. And there is some sort of hand-wavy explanation which say that if you're conditioning in latent space, that can be more successful in the sense that your latent space is a sort of semantic or representation of your input, whereas conditioning in, say, raw input space can be a bit tricky because your conditioning has to learn how to link, say, raw pixel values to like your high-level abstract thing, like. Yes, I think like that's the idea with these latent diffusion things. Like people have been, at least in images and video, it's been very successful to condition latent models, whereas it's much harder to condition, say, pixel level generative models. So just to show you guys some experiments, and like the main idea of the experiments I'm going to show is we follow like standard benchmarks in the field because we were introducing a new architecture, so we want to compare it to what's followed or what's been there before. And the main idea of the experiments is to see if we really benefit from this joint trimming, this notion I was talking about of like unifying different data sets and so on, and see if that has any sort of improvement here. So the dream would be sort of to sample the entire chemical space, right? Like we know that there are lots of data sources of 3D sort of crystal and molecular type data. And we'd love to train like a humongous model on all of them. But in order to demonstrate this notion of transfer learning, we picked like two like conventional benchmarks in the field. For small molecules, we used QM9. And for crystals, we use Materials Project. So QM9 has around 130,000 small systems of up to 9 heavy atoms and sort of all possible like combinatorial systems, and their structures determined with the DFT. And Materials Project has experimentally used crystals which are candidate materials, and we use a subset of it with 45,000 or so. And their structures are also mostly experimentally determined. So I'll show these results a bit quickly. Like for instance, like we want to generate physically realistic and stable crystals with our model, and there are like simple physics-based checks that you can do to check whether they're structurally valid, whether the atomic composition is valid. And you can also run DFT on your generated samples, so the kind of crystals you're generating, and you can compute some sort of notion of stability for them. This is based on like some energies above theoretical hull computed from your training set. But essentially, like you could think of it as run DFT and come up with some notion of how stable your output is. So we compared two different methods here in this slide. I'm showing you all the metrics as well as these methods. One is an equivariant diffusion model only for crystals. Another is a language modeling based approach. And you can see like how they perform, like they kind of improve in each generation. So, the second one is an improvement of the first one. And generally, the stability rate seems to be an important metric. Like the models may not generate very stable crystals. Now, when we sort of took our model and trained two versions of it, one which uses a graph neural network, which was the equivariant ADiT, and the other which uses a transformer, which is the green one, just ADiT. We could see that we attained results which are really close to the state of the art. And we also saw that the sort of transformer model, the one which kind of used data augmentation to learn the symmetries, was doing better. But these models, by the way, are only trained on materials. So the main thing, like the main message was like when we train on both molecules and materials, the jointly trained model generally matches or gets better than the model that's only trained on materials. So there's like some small evidence or some sparks of transfer learning here. Similarly, here's what like these outputs may look like, and it's hard to like gauge anything about them, but just an example of some outputs. Similarly, like for molecular systems, right, we again want to check very similar things. So simple physics-based checks for whether the structure generated is valid, as well as we can see if the molecule has a valid SMILES to check if RD-Kit can find something valid for it. And some of the checks we use basically look at whether your generated samples have like very energetically unfavorable configurations, or whether there are clashes, steric clashes within them. So simple checks, but the idea is to see if our models can do these basic things as well. So here for the results, again, like we compare two very similar baselines, like variant models as well as language models. And then like when we look at our models, again, we see similar messages. We see that firstly, using pure transformers compared to equivariant GNNs is better empirically. And we also see that transfer learning, again, benefits, especially in terms of validity. I think here, like for this molecular benchmark, the metrics are quite saturated, I would say. But generally, like we could see that at least like training jointly was leading to a slightly better generative model overall. And here are just some samples, like here's what like the model's outputs look like. Another thing that's worth saying is like, we compared to these equivariant diffusion models, this previous generation of models, they're also quite slow. So what this plot's showing is that it takes a lot longer for much smaller equivariant diffusion models to generate the same number of samples as a pure transformer. And what this allows, right, is that you can now scale up your transformer models. And we went up to 500 million parameters. Whereas this is not possible today with equivariant GNNs. Like it's just too hard in terms of engineering. Theoretically, obviously it's possible, but like the important point here is these equivariant GNNs, they've been studied for a long time, including by myself, and they're really interesting mathematically. But there's something about the engineering, like the implementation, that makes it really hard to scale them up on multiple GPUs. And now, as people are realizing that when you scale pure transformer models, you can benefit a lot from the engineering that, say, NVIDIA has already done to optimize them. And it seems that when trained at scale, you can learn a lot of these mathematically nice inductive biases and symmetries that people were previously trying to hard code into their models.
Sorry. Engineering.
I think it should be feasible to accelerate gene. I think this, are you familiar with this notion of the hardware lottery for deep learning? So it says it proceeds as follows: GPUs and transformer architectures are such a good match for each other that transformers have won the hardware lottery. And that means that 100 times more effort is now being poured into accelerating transformers. But that doesn't mean that they are outright the best, most universal architecture. It could be that different forms of hardware could accelerate other deep learning workflows. So, for instance, graph neural networks and other graph-based workflows, not just GNNs, they could be accelerated by something called it's called an IPU. It's from a company called GraphCore. It's being developed right here in Cambridge. And the idea is how do you accelerate sparse computation? The thing with GPUs is that they do dense matrix multiplication super fast. But GNNs and graph-based workflows are based on sparse matrix operations, right? So there are companies actually trying to build this. And I think we shall see, right, what wins out. But currently, transformers are super powerful. Yeah. So then, that allows us to scale up our models, and we start to see some preliminary evidence also of scaling laws, which essentially say that when you train language models at small scale, you can predictively say what will be the performance when you scale up to humongous networks. And we were starting to see some evidence of these kind of scaling laws for our molecular models as well. And I think that's again a positive sign, which encourages us to say, okay, we should then try to really scale up the data and the models here. And I think just to close off this section, I think it's worth saying in this talk, we observed something like this, that if you train for really long, then your transformer-based network starts performing the chain. But if you're in academia and you don't have a lot of GPUs, you may be stopping training much earlier. And it's also highly dataset dependent. So maybe the best models are the ones that you can train. And the goal of building models is to solve real problems. So this was one of the learnings for me as well, kind of working in academia versus working in industry as well. Because as I said, I was really invested in this field of GNNs as well. And I think some of these, doing these kind of experiments was really breaking a lot of my own personal intuitions as well about this research.
Do you think this has anything to do with the limitations on model size with GNNs? So the transformer here, is that a lot bigger in terms of number of parameters?
Yes. I think basically no one has trained a 500 million parameter equivariant GNN today because it's just it would be too slow. Like even if you can do it, it would like iterate very slowly and be extremely cumbersome. So like we haven't done it yet, right? And that's a good point, right? Like there's no theoretical reason why we can't. It's like an engineering
It's like
bottleneck.
if you condition this plot on number of parameters,
Yeah.
would you still get this?
I think like if you could scale up, right, to billion scale equivariant GNNs, then I mean, I don't know. I think, nowadays, like, there's this notion of matching parameters, which is one way to do this comparison. Another way is matching flops, floating point operations. And I think again, like what might happen is that for the same number of flops, you can have a lot more parameters for your transformer model. And that may mean that it could again win out. But I think like obviously someone needs to do these experiments more carefully. Like that's why this is a random kind of hand-drawn kind of plot instead of something more rigorous. I'll skip some of this stuff. I'll quickly like conclude. So this is just a summary, like which says we built a generative model which would unify the generative modeling molecules as well as crystals. And how we did this was using this notion of latent diffusion. I think like there's some new ideas here which are basically around like how you can have multimodal data that you can project to latents. I think that's a new idea. And then like doing this generative modeling or unified generative modeling in latent space as well. Basically allows us to have a potential architecture which could be a foundation model or a scaled up generative model across chemical systems. So what's next, right, is essentially like this paper is just about architecture and is a bit unsatisfying in that sense. You have your model is the bold one in a table, but that's that's only where the story really starts. And I think to do something practically meaningful, we would need to collaborate with scientists and essentially build in these notions of conditioning or guiding generative models based on experimental properties or based on essentially concrete scientific design tasks or design scenarios. And the other thing is obviously like we want to scale this system up, and that requires really good engineering. That requires curating data from all kinds of sources for molecular systems as well as crystals. And essentially, that's no small feat in itself as well. So I think like this kind of works are just the start. But I do feel quite excited about the possibility of these foundation models for chemistry and them becoming essentially tools for scientists to do something new or like unlocking new insights for scientists. So that's it. Thanks for listening and happy to discuss.
Something which I would kind of enjoy hearing about is when you went into this work. So for reference, Liao and I work on the same project and work with Petra. So naturally we're using graphs, at least in the initial implementations. What would be interesting is when you went into this work, did you have the sort of transform architecture which you trended towards in mind, or did you go in with the graphs, saw the perhaps limitations or the difficulties of all those kind of inductive biases, and that's what trended to the final solution?
Yeah, I think like when building this project, it actually started with like I wanted to do this plot in a rigorous way, I wanted to find this out. So that was the origin of the project. AlphaFold 3 had just come out, and one of the big messages of AlphaFold 3 was that you can remove physical symmetries. I think not graphs. Like I think AlphaFold 3 still uses some notion of locality actually, but it talked a lot about removing these 3D symmetries. And I wanted to find out because I've been working a lot on those. So I wanted to find out like whether there's a scale at which you can remove it. What's that scale? And we quantify it. So that's how it started. Obviously, then how you tell the story in the talk and the paper is completely different, right? But we did try to be like when we set up the code and when we try to ablate it, we try to really like fairly compare GNN based versus transformer based system. I think like, the other thing, right? Like the question of whether you should use a transformer or a GNN, I think it depends on your task. Many times, if your data has a lot of nodes or a lot of atoms or a lot of nodes, then using a transformer may become really unfeasible. And that locality of a GNN really helps, especially in terms of GPU memory usage, right? Like if every node in your input only needs to interact with a subset, that's going to use a lot less memory than if every node needs to communicate with every other node.
Yeah, I find at least with work which we're doing, it's kind of difficult to inject meaningful inductive bias, right? So you kind of trend to this big graph attention network, where everything's really connected. We're just trying to learn the relationships. So this kind of it seems really attractive in some ways.
Well,
under those,
a graph attention network is a transformer, right?
Yeah.
It's the same kind of mathematics using thing. Yeah. It works that way. I think like even like the AlphaFold type system where they're taking in a sequence and then outputting a structure, they need to figure out the connection between every part of their input, right? And hence they use transformers also. I think it depends a little bit on your problem as well, like on what you're kind of trying to model and so on.
So, transformers symmetries or something?
Yeah, so just data augmentation. So when you put an input as a training sample, then you can just apply a rotation to it, and over the course of training for 1,000 epochs, the model is going to see the same input in many different orientations. So
you apply transformations. Okay.
yeah.
And the GNNs you mentioned now, you have, so the start with your model, you have the VAE, frame, freeze, and you have the latent transformer. I also mentioned transformers with symmetry, so I thought you have better transformers.
Yeah, so the VAE has to use some architecture, right, within it. And basically, like the encoder and decoder of the VAE could be a GNN or a transformer. If you use an equivariant GNN, then your latent space would be sort of having those symmetries built into it by design. If you use the transformer, then your latent space would potentially also have those symmetries, but like a bit more softly, right? Like it's a learned kind of symmetry.
I have a question about the real world application of these models.
Yeah.
What kind of use cases do you envision, and what do you think is the right way to validate them, especially in this space where you're doing multiple things at the same time? Like, do you need multiple validations for parts, or would you validate a model as a whole?
I think so. I think like it's, as I said, like this kind of is really unsatisfying because, like, especially with generative models, it's really hard to evaluate whether they're useful unless you go to the wet lab, right? So we've started seeing some validation for like, especially for generated proteins from other diffusion models, but some generated small molecules, some generated crystals as potential candidate materials. So these have been done independently, right? Obviously, like if we ever like carry out the full vision of this work, we would like to validate, we would like to validate experimentally all these things. I think those kind of efforts would require a big team. Like realistically, when you look at any of these experimental papers, they would do like one design project, like one campaign, and that would be a huge team effort. So, like every design campaign is a new scientific problem, right? So, like, yeah, I think it requires good collaboration and it requires like coming up with projects. So concrete ones, right? For instance, are like if you think about protein design, I think there are lots of examples. Like you just need to see like what the Baker lab is doing. For small molecule stuff, specific targets, right? And they may or may not have the structure of that target. And we could think about like these models as potentially being a new generation of structure-based drug design tools. The challenge there is of synthesizability of what your model dreams up.
Yeah.
But I think people are working on that aspect as well. Again, for like crystals generally, like you may have some very specific properties you care about for your crystal, and you can like condition your generative models to dream up crystals with roughly those properties. And again, the challenge with crystals also is synthesizability. Like you may theoretically have like some composition of elements, but in practice, whether you can realize that or you end up at something very different is often very difficult. But I think people are making efforts.
Is Meta going to be the one to validate this kind of thing? Or?
I think for the crystals, like as I said, right, like they work on these VR headsets. So like for instance, you can imagine like the glass that's used in VR headsets currently is very heavy. You can find lighter display materials. These are called organic solid crystals. Then that they are actively working on and validating. Like they literally build these things, like so they have all these set actually.
Yeah, and it's a very specific use case.
Yeah,
Very specific things that they're probably measuring, like the weight,
yeah.
whatever other properties.
So I think like also battery materials as well, I think is generally a very important topic for many people, right? Like if you can have batteries with longer life, shorter charge cycles, that would be a big deal for so many. I think people are quite interested in these approaches.
It's really cool. Don't think there are any questions online. So let's thank Chaitanya one more time.
Space lab, your piece.
Yeah. Oh, yeah. It was like what that slide was saying, right? Is essentially like we did some of this. We did some of these like unified generative modeling stuff, right? So we want to see like whether the latent space that we are generating is something interesting. Yeah. So here we are plotting latents per, and then like we're coloring them by atom type, and then the size says whether they are from a data set or whether they're generated. Smaller ones are generated, so they're big. And then system is like circle is whether it's crystal and cross is whether it's molecule. Then like I think the first principal component is like along the x-axis and which is y. And it's very simple. Like the first principal component kind of shows that all your molecular stuff, right, is like roughly within like this range. But I had other plots in the paper which were showing that like other elements from crystals were like more spread out. And then the second component, which is the y-axis,
does kind of cluster along the atom type as well, like in a very visual way. And then like some notion of transfer learning you can see from, for instance, like all the oxygen atoms from both crystals and molecules are embedded together, but there is like some difference in them. So this just sort of thinking about how the model could be learning, or because like one of our hypotheses was the model just embeds crystals and molecules completely separately. There's like no like it kind of learns two tracks within itself.
But I think like these plots were showing that that's not necessarily the case. I mean, there's at least some transfer learning.